Hey guys, I want to begin this video just going over some basics behind a really important concept in calculus called the derivative. Um, we want to first begin by talking about slopes and average rates of change. You have done slope in the past, and most everything that you've done with slope has involved a straight line. So if we had a line, I'll just draw one right here. We could find 2 points on that line and we could calculate the slope or the rate of change and some average rate of change or between these 2 points, or sometimes you've heard it called rise over run. How much are we rising to how much are we running? And basically the slope measures the change in y with respect to the change in x, and sometimes that can be written as the change in y with respect to the change in x. And so you've talked about that concept and worked problems and learned about this concept since middle school. Then when you got into probably geometry and algebra 2 and maybe even in algebra 1, we began talking about the slope of maybe a quadratic. So for instance, if we had a point on our parabola at x equals 1, then maybe a point here. In algebra 1, we talked about the average rate of change here. So we would use this line to approximate how fast that curve is changing between those 2 points. And you may remember it as the average rate of change, or AROC. So you have calculated the slope involving curves in the past, but it always was just an average. Calculus is much more dynamic. We want to actually, in calculus, or use calculus, to find the slope at one single point. So if I had the point at x equals 1, and I draw a tangent line, remember a tangent line will intersect the curve at one point. That's a concept that you learned in geometry. But if I wanted to find the slope at one point, well, how am I going to do that? That would give me how fast the curve is changing right here at this one single point. But as you may recall from your previous math classes, to find the slope, you actually need 2 points. That's why we've always done the rise over run, or the average rate of change. We've always calculated that slope with 2 points. What we want to do now in calculus is find the slope at 1 point. What is the slope of this curve? How fast is the parabola changing at this one particular moment on the graph? So we're going to I'm going to explain to you in this lesson the whole idea and the concept of how we could go about doing that. The slope of this line that I have here is it's called the average rate of change, but the slope of this line is a secant line because it goes through where x equals 1 and where x equals, this is about what, 1 3/4. This is called a secant line because it goes through 2 points on the curve. We could find the slope of that secant line, but as you can tell graphically, the slope of this secant line is nowhere close to the tangent line, the one that's drawn in orange. So what we might do is we move a point that's a little closer, and then maybe we could find the slope of that line. It would be a better approximation for our tangent line, but it still wouldn't be exactly. So the idea is that we could find the slope of this secant line, then maybe this secant line, and then we just keep moving this point closer and closer so that our secant line and our tangent line are so close that they almost eventually become indistinguishable, that the secant line and the tangent line become one. So we're watching the slope change as we move this point closer and closer and closer and closer and closer to the point of tangency. As the change in our x values gets smaller, 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 what is this secant slope approaching? So that's the idea, and we could think of this as a limit, right? Because we're moving this point closer and closer and closer and closer, and we're trying to watch the secant line change and ask ourselves, what is it slowly becoming as we approach that point of tangency? So this is a big idea. It's called the tangent line problem in calculus, and we want to use the secant line to approximate the slope of the tangent line. Okay, so I'm going to scroll on down and we're going to talk through an algebraic analysis of doing this. So let's take this function, for instance. This is f of x equals 3x minus x squared. And I want you to find the average rate of change. Okay, so average rate of change uses 2 points. And that would be the slope of the secant line. Okay, so what I'd like for you to do is I'd like for us to talk about the slope between this point, 1, f of 1, and this point, which we're going to call 1 plus h, and f of 1 plus h. Okay, now h is going to be defined as the change in x between two x values. So h is the change in x. That means we want the slope at 1. We want to think about what is that slope at 1. So we're going to pick another point close to 1 that moves over h units, and we're going to find the secant slope between those 2 points. Now you may recall from Algebra 1 that to calculate the secant slope, we use the formula y2 minus y1 over x2 minus x1. That's that change in y over the change in x. So I labeled my points that are given to me, x1, y1, x2, y2, and I want to calculate the secant slope. And I'm going to call this secant slope a of h. So y2 minus y1 over x2 minus x1. Now we can clean this up. Okay, so these 1's will cancel and we'll be left with an h in the bottom. And then we need to understand that this f of 1 plus h can be calculated. This is asking us to take 1 plus h and plug it into f everywhere we see an x. And then f of 1 is asking us to take 1, plug it into f everywhere we see an x, and see what we get. So let's do that. If I plug 1 plus h in for every x, that'll give me 3 times 1 plus h minus 1 plus h quantity squared. So notice that up here in my function, I had an x here and an x here. 3 times x and then minus x squared. And that's what I did. 3 times x minus x squared, but I changed the x's to 1 plus h. Now I have to subtract what I get when I plug in 1. Well, I'm just going to plug in 1. 3 times 1 is 3 minus 1 squared. So this is really 3 minus 1, or 2. And then it's all over h. So we need to clean this up, distribute our 3. We need to FOIL this out and distribute our negative at the same time. So that's going to be minus 1 minus 2h minus h squared minus 2 all over h. Okay, so let's see. 3 minus 1 minus 2. 3 minus 1 is 2. Minus 2 more is going to be 0. So all of these constants make 0. And then I know the 3h and the minus 2h could combine to give me 1h. So I actually have h minus h squared over h. And then I could factor an h out of the top since it has that GCF. Put it over h, and then those are gone. So my final secant slope, a of h, is 1 minus h. Okay, so then the next question is saying what happens to the secant lines between the points 1 f of 1 and 1 plus h f of 1 plus h as h gets smaller and smaller. So that's that whole idea as we were talking about before. This change in x, if I pick this point first, then I pick this point, then I pick this point. H is getting smaller because H is that change between those X values. So H is getting smaller and smaller and smaller. So what's happening to the secant line is that it's slowly becoming the tangent line. All right, so what we want to do is take our expression for A of H, which is 1 minus H, and we want to take the limit as H goes to 0. Because H is getting smaller and smaller and smaller, the secant lines are becoming the tangent. And so if we take the limit and ask ourselves, well, what is the value of that secant slope as H gets smaller, smaller, and smaller and approaches 0? We can plug in 0 for H through direct substitution and we get 1. So what this is saying is that back here on our original curve, the approximation for that tangent line, which was originally orange, the approximation for the slope of this line is 1. We're saying as H gets smaller, 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 that secant slope's getting closer to 1. So the slope of our tangent line is 1. Okay, now what we did is we found the slope at 1, but what would be even better is if we could find a slope at multiple points. So for instance, what's the slope way over here at 3? What's the slope of the tangent line there? Or there? Or there? Or here? Right? So we want to be able to find the slope of the tangent line at lots of values, not just at 1. Going through this process would take some time, and it would really be efficient if we could find a way to express this slope in terms of X so that we could find the slope for any X value. And that's what I'm going to go over in the next video.